Welcome everyone, and thank you for joining today's webinar on corrosion testing for medical devices. Our presenter is Dr. Kin-Ling Sham, Senior Consultant Metallurgist and Manager of Corrosion Testing. Dr. Sham has more than a decade of experience in metallurgy, welding metallurgy, material characterization, non-destructive testing, and failure analysis. Our question moderator is Dr. Michael Liao, Laboratory Manager, and I'm Melissa Campbell, Marketing Manager, assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees are muted. However, if you have questions during the presentation, please enter them in the questions section located in the bottom of your control panel or in the app. And if time permits, we will answer these questions at the end of today's event, or we will follow up with you in the coming week. At the end of the webinar, a survey will pop up on your screen and your feedback is greatly appreciated. Now I will turn it over to Dr. Sham.
Thank you, Melissa, for that introduction. Here's a brief outline of today's webinar. I will give an introduction to EAG for those of you not familiar with us. Then I will cover the most common corrosion tests for medical devices that the FDA requests, ASTM F2129, equipment and test setup related to ASTM F2129, digital images taken before and after corrosion testing, how to interpret cyclical polarization scans, and what to expect in the final report, and what can Eurofins EAG do to help me improve the corrosion resistance of my medical device. We will also briefly go over other standards for medical device corrosion testing at Eurofins EAG. And then we will end with questions and a Q&A session. Please send in your questions using the app or the control panel on your screen. So now I'm going to move forward and give a brief introduction to EAG. Eurofins is a global leader in testing with more than 5,800 employees, 900 laboratories within 54 countries. EAG is a division of Eurofins specializing in materials testing. We have more than 1,000 employees in 20 laboratory facilities around the world and support over 5,000 clients with 2,500 different types of testing equipment. Our metallurgical team is based in our Los Angeles laboratory. The LA team has been solving challenging projects requiring expertise in materials science, electronics, failure analysis, metallurgical testing, and destructive physical analysis since 1972. We perform failure analysis and custom testing for metal components in a variety of industries. Additionally, we assist clients with product design, material selection, product improvement, legal consulting, and quality assurance programs. Now let's take a look at the SMART chart. SMART is an acronym for Spectroscopy, Microscopy, Analytical Resolution Tool, and it shows the techniques we have at EAG. This SMART chart allows us to compare the spot size and detection limit of each technique. The techniques are color-coded according to the descriptions at the lower left. For example, dark blue areas provide elemental information, primarily, while green shows imaging information. The x-axis shows the range of spot sizes from 1 centimeter at the right down to 1 angstrom at the far left. The y-axis shows concentrations either in atoms per cubic centimeter at the left or in atomic concentrations at the right that range from 100% at the top down to 10 parts per trillion at the bottom. So within the box, you can select your technique based on the detection limit you need and the size of your area of interest. Outside the box are techniques that don't quite belong in the chart. The techniques on the right, for example, don't necessarily have a spot size associated with them. They are basically bulk composition techniques. They may consume your entire sample, and they have the detection range shown from top to bottom. Corrosion testing will be in the bulk techniques. The techniques at the bottom are basically imaging techniques and don't provide compositions per se, but they do have relevance with respect to the spot size on the x-axis. An interactive version of this chart can be found on our website at eag.com/techniques. So what is the most common corrosion test for medical devices the FDA requests? Well, let's begin. The FDA, which is called the Food and Drug Administration, is an agency within the Department of Health and Human Services. They are responsible for regulating the safety and effectiveness of medical devices. Medical devices include a wide range of products, from simple items like bandages to complex technologies like implantable pacemakers. The FDA recommends conducting ASTM F2129 for testing corrosion susceptibility of implantable medical devices, using the most current version at the time the testing is executed. Testing should be performed in the final form in which it enters the body, after subjecting the medical device to simulated assembly and implementation, which includes compression, loading, and deployment of the medical device through an in vitro fixture that mimics in vivo anatomic conditions. Alternatively, comparable stresses, strains expected in vivo can be simulated. The worst case in terms of corrosion susceptibility based on surface area, size, and/or geometry should be tested. The appropriate sterilization process will also need to be performed on the medical device prior to corrosion testing. The corrosion testing of the device is intended to test the final form, final surface finish, device size, and clinical conditions of the device at the time of implantation. The goal is to replicate the same conditions and environment the device will encounter in the field. The FDA recommends at least 6 samples to be tested to evaluate the known variability of corrosion performance. More samples may be needed depending on the corrosion testing performance of the device and the acceptance criteria that has been established by the medical device manufacturer. So let's talk a little bit about the equipment and setup of ASTM 2129. Eurofins EAG Corrosion Testing Lab executes ASTM F2129 using a Gamry reference 3000 potentiostat, as shown on the left here. A Gamry multi-port corrosion cell kit is used for the testing of the medical device, as shown in the center. A reference electrode in the form of a saturated calomel electrode is used. A working electrode is built to hold the medical device to be tested. Working electrode, reference electrode. A gas diffuser, here's the gas diffuser back here, is used to deoxygenate the testing solution prior and during the corrosion test. A graphite counter electrode is also used. All equipment is visually inspected prior to each set of tests performed to ensure they are in good working condition. The saturated calomel electrode is checked to ensure low impedance prior to every set of tests to maximize potentiostat performance. In accordance to the 2019 version of ASTM F2129, the most current version, the cyclical potentiodynamic polarization test specifies that a specimen be exposed to a specific solution comparable to the environment of the human body that the medical device will be implanted in. The most common testing solution is phosphate buffered saline solution, also known as PBS, which mimics blood plasma. Using PBS as the testing medium, 500 milliliters of PBS is placed in a 1-liter Gamma multiport cell and purged with high purity nitrogen, 99.99%, at a flow rate of 150 centimeters cubed per minute, which is 0.15 liters per minute, for a minimum of 30 minutes before the commencement of the corrosion test. During the test, the nitrogen is turned down to minimize bubbling in the testing medium and subsequently on the medical device being tested. The temperature of the solution is maintained at 37 degrees Celsius plus or minus 1 degrees, consistent with the temperature of the human body. All corrosion testing is performed inside a Faraday cage to minimize external noise that could affect the final data output, as seen on the right here. So prior to the commencement of each corrosion test, the medical device is imaged using a Kionce VHX 7000 with magnifications up to 200x. The goal of the digital images is to capture an overall picture and specific areas that are more susceptible to corrosion damage prior to corrosion testing, and compare them with the same digital images after corrosion testing. Here, we see a material before and then a material after corrosion testing. It can be seen that after corrosion testing, the corrosion damage shows discoloration, white byproduct, and corrosion damage to the material. So let's look at the cyclical polarization scans and talk about how to interpret these scans. So this specific scan here, this cyclical polarization scan is consistent with a material surface that possesses corrosion damage. Here we see the x-axis is logarithmic current density in amps per centimeters squared versus the potential, which is the voltage versus the saturated calomel electrode or the reference electrode here, however you want to, in volts. For executing ASTM F2129, a resting potential is obtained at the point where the voltage is stabilized at 3 millivolts per minute. Okay. For this scan, the resting potential is 0.107 volts. The resting potential is defined as the potential of the working electrode relative to the reference electrode measured under virtual open circuit conditions. The scan begins at the resting potential and moves in a noble or anodic direction until a breakdown potential is reached. The breakdown potential is the least noble potential at which corrosion damage will initiate and propagate. The breakdown potential is 0.725 volts in this scan. An increase in the resistance to corrosion damage is associated with an increase in breakdown potential. The scan then continues to a current density threshold 2 decades greater than the current density measured at the breakdown potential, until the vertex potential, which is 0.793 volts for the scan, is reached. The vertex potential is either a preset maximum voltage or until the current density reaches a preselected maximum magnitude. In this case, it reached the preset maximum current density. Then the voltage is reversed to the final potential, which is also the resting potential in this case. The final potential for ASTM F2129 corrosion testing sets the final potential to the resting potential. The corresponding current between the working electrode and counter electrode is recorded and plotted as the cyclical polarization curve. So remember, I said this scan specifically here is consistent with a material surface that possesses corrosion damage, okay? This is considered a positive hysteresis and occurs when corrosion damage initiates and the passive film damage is not repaired. A quick word on the scan rate. ASTM F2129 recommends using a scan rate of 0.1667 or 1 millivolt per second. So typically here at Eurofins EAG, we use 1 millivolt per second for testing, unless a slower scan rate is needed for more detail or stability of the instrument. So let's look at another scan. So this cyclic polarization scan is consistent with a material surface that possesses no corrosion damage. The scan has a resting potential of 0.043 volts. And it moves in the anodic direction. There is no breakdown potential, as we can see. The vertex is the preset maximum voltage of 0.8 volts, where the scan is stopped and reversed to the final potential. For this scan, the final potential is set to the resting potential, which is 0.043 volts. So let's look at a different scenario of a cyclical polarization scan. This cyclic polarization scan is consistent with a material surface that initiated corrosion damage, but then repassivated the film to some extent. So the scan here has a resting potential of 0.037 volts. So as it moves towards the anodic direction, we see this metastable pitting event occur before the breakdown potential at 0.166 volt. And then what happens? You see it go out and come right back in. That means it immediately repassivates. The scan continues to move forward and the breakdown potential is reached. This breakdown potential is 0.201 volts here. Now the sample corrodes and then further corrodes, and it reaches the vertex potential of 0.662, where the scan is stopped at the preset maximum current density. During the reverse scan, a negative hysteresis is formed where the reverse scan intersects the forward scan. Now we see the intersection portion here at a value that is less noble than the breakdown potential. The protection potential here is 0.362 volts. The difference between the protection potential and the breakdown potential display the range in which corrosion damage can occur here. For this scan, the final potential is set to the resting potential, which is 0.037. So the takeaway from this scan is that this cyclical polarization scan is consistent with a material surface that initiated corrosion damage, but then repassivation occurred. So the rebuilding of that passivation film to some extent occurred. But if you look at the characteristic of this cyclical polarization scan, there is extensive damage, corrosion damage to the surface. So the quality of the repassivative film is questionable. So after we do all the testing, we will provide a final report. Here's a list of all the criterias and all the information that is provided in the final report. We will tell you the general type of medical device, the material type, the sample name, identification, and quantity tested, the sample metallurgical condition and surface finishing, sample surface area, general description of corrosion testing procedure executed with specific scan rate and testing medium used, digital images before and after corrosion testing, resting potential, breakdown potential if there is one, the protection potential if there is one, the vertex potential, and the final potential. The pH of the test solution before and after each test will be provided, in addition to any comments relating to the testing medium quality, such as if the fluid is still clear or if the fluid is cloudy. The cyclic polarization curves will be individually provided. In addition, a combined cyclic polarization curve for each type of testing medical device done will be provided to look at the comparisons of all of them. And general observations related to corrosion for each sample tested will be provided in the final report. So what can Eurofins EAG do to help me improve the corrosion resistance of my medical device? So a few things that we offer include several other techniques. So Eurofins EAG Lab can further characterize the surface of the medical device by using a scanning electron microscope, SEM, with energy dispersive spectroscopy, EDS, to capture images of the surface before and after corrosion testing at magnifications well above 200x. This will reveal tool marks, microcracks, and any surface defects from insufficient electropolishing and other manufacturing techniques. EDS analysis can be performed to provide elemental makeup of corrosion byproduct on the surface and at areas with corrosion damage. Another useful tool to mention is Auger electron spectroscopy, which analyzes a small area of the thickness of the oxide layer formed to protect against corrosion. This oxide layer is often further developed using a passivation technique to enhance the corrosion resistance of the medical device. Auger analysis can assist in determining the consistency of the passivation techniques in multiple areas within one sample or one specific area across many samples. Additionally, failure analysis can be performed on the medical device to determine what is causing the premature failure and corrosion and subsequently provide information and recommendations to mitigate or minimize the failure and corrosion. Additional testing can be performed after changes have been made per the recommendation to ensure the failure and corrosion is minimized and improved. So going back to the Auger technique, we have a pour electropolish here. So the takeaway from this graph is here you have the x-axis is the depth and the y-axis is atomic concentration. So here you can see that iron is fairly high on the surface and it's above the chromium. So iron is the surface oxide layer is not chromium oxide rich. For a good electropolish, here you can see that chromium is higher than the iron. So you can see that the chrome oxide layer is approximately 20 angstrom in terms of thickness. So other standards for medical device corrosion testing at Eurofins EAG include this ISO 10555 Annex A. This is a standard for intravascular catheters supplied in the sterile condition and intended for single use for any application. When corrosion resistance is tested in accordance to this method, metallic components of the catheter intended for fluid path contact shall show no signs of corrosion. In accordance to Annex A of this method, the catheter is immersed in sodium chloride solution, then in boiling distilled water, and afterwards examined visually for evidence of corrosion. So the testing follows that the medical device is immersed in the saline solution at room temperature for 5 hours. Then the device is removed and immersed in boiling distilled water for 30 minutes. Then we allow the water and the device to cool to 37 degrees Celsius in room temperature, and we maintain the 37 degrees Celsius for 48 hours. The device is then removed from the water and dried at room temperature. It is then inspected visually for signs of corrosion. Digital images, photo images will be taken before and after corrosion of this corrosion test to demonstrate signs of corrosion. The test report contains the identity of the catheter, a statement as to whether corrosion occurred during the test, and like I said, photo documentation of the device before and after the test. Another medical device corrosion testing standard that is often executed here at Eurofins EAG is ASTM F1089, a test method that tests and evaluates new and reusable surgical instruments fabricated from stainless steel alloys for corrosion resistance. The Boyle test is applicable to martensitic, austenitic, ferritic, and precipitation-hardened materials to detect surface imperfections, free iron, or other anodic surface contaminants on the stainless steel. The copper sulfate test is used to detect the presence of free iron on the surface of materials. If iron particles are on the surface, the aqueous copper ions will react with the free iron particles and create an oxidation reaction resulting in copper deposits on the surface. If this is observed, then the test has failed and the material has an unacceptable amount of iron present. So as you can see, the Boyle test is used for austenitic materials, class B, precipitation hardened materials, class 5, and ferritic materials, class A, containing 16% or more chromium. So in these three incidences, both the Boyle test and the copper sulfate test must be executed. If your stainless steel for surgical instruments fall in Class 4, which is martensitic materials, or Class 6 ferritic materials, but containing less than 16% chromium, then only the Boyle test is applicable. Lastly, we also perform in-house overflow corrosion tests here at Eurofins EAG. So if you have any internal quality control corrosion tests where you need help, we can assist. Or if you have any custom corrosion testing that you need validated by a third party, we can also assist. These are the references that were used. And I am going to hand it over to Dr. Michael Liao for the Q&A session.
Thanks, Kinling, for the informative webinar and discussion about FDA testing on medical devices and specifically about the ASTM F2129. So like Melissa and Kinling mentioned, if you have any questions about the webinar, please feel free to use that questions panel in the app. So one question that we received is there a time scale for this plot, or how long does a typical cycle take?
Is there a time scale for the plot? And what is the typical, what was it?
How long does a typical cycle take?
So there's a range of time that this testing can take. So the cyclical polarization scan, what it does is it essentially runs voltage through your medical device, and then it reads out it reads out the current with respect to that, right? And so it depends on the material that you're testing, the manufacturing conditions, and also the surface finish of your sample, okay? In corrosion testing, it's dependent on your sample. So if for some reason there is a, I guess, you know, if for some reason, say your medical device did not have a was not passivated. So typically most medical devices are passivated. So there's this thin, perfect oxide layer that we test. So we can test it, it's a robust layer, right? And we can test it at 1 millivolt per second scan rate. So the test for those, in general, regardless of material, what I've seen is it's taken about anywhere from an hour to 2 hours, right? However, if you then don't passivate your material and for some reason the surface of your material creates like a capacitance double layer, right? Your instrument just doesn't have that stability. So if we run it at 1 millivolt per second, like we will not get the resolution that we need to see everything, or the instrument won't be as stable. So then typically we have to run it at a much slower scan rate, which typically takes twice as long. So the answer just really depends on your material and the condition of the surface of your material.
Okay. Another question that was submitted was for SEM EDS, how would we prepare a sample out of a catheter or an embolization coil?
I guess we would, the catheters typically we can coil up and specifically look at the areas that we want to pinpoint in the SEM. So we'll look at everything in the keonts, right? So the keonts typically goes up to about 200x in magnification. Using that, we can determine the general area we want to look at, and we place it in the SEM. So there's no sample preparation really needed unless the sample is much larger than our chamber allows. And typically in terms of medical device, I have not found that to be a problem.
Right, and I guess I could just expand a little bit upon that as well. As Kinling mentioned, our SEM chambers tend to be quite large, and so medical devices are generally going to fit inside of our SEM tools. The chambers are also typically equipped with what's called low vacuum mode, so we can put samples in or biological type samples in and not have to worry too much about not reaching a set vacuum, but still being able to get good imaging, and in most cases still getting decent SEM EDS data out of it. In cases where a sample is not behaving well in an SEM, either in high vacuum or low vacuum mode, we can always slightly coat the sample with an iridium or some other metal thin film that will help with charge dissipation. The film is generally going to be thin enough that we will look right through it in SEM EDS and still see contaminants or other chemical species on the surfaces. I hope that answers your question. Another question that came in is, what device size limitations do you have for F2129 testing?
So we don't have much limitations. We actually accommodate for a variety of dimensions, unless it's like 6 feet by 6 feet. So I would say most medical devices will fit in our 1 liter multi-port cell. So I believe the diameter of that is about 4 inches. Additionally, we have accommodated for much longer samples by building custom setups for different sample sizes that are longer than 4 inches or 3.5 inches. So we don't have too much limitation. We have experience in accommodating and building different setups for different size and shape medical devices.
Thank you. If you have specific questions about your product, feel free to contact us with specifics, and we'll be happy to chat with you about that. Let's see, next question. In the ISO 10555 test, what is the purpose of immersion in boiling water? Is it to induce thermal expansion of the sample or to initiate, propagate any pitting that may have occurred during the saline soak?
I believe it is to exacerbate any pitting that has occurred in the saline soak.
Okay, let's see. Lots of questions here. Let's go right ahead and do the next one. How does a passivation thickness affect the result? If the passivation is not homogeneous, how will the curve look?
How does the passivation thickness affect the results? So if the passivation is inconsistent throughout the medical device, right? You have some areas that are a little thinner, some that are thicker, or some that are not chromium oxide rich, maybe some that are more iron rich areas. So those areas are going to be more susceptible to corrosion damage, and that will initiate faster during the ASTM 2129 corrosion test. And if
Would
you
you
have,
expect
go on.
would you expect to see a difference in breakdown potential if that occurred?
I believe so. I mean, like I said, the higher the breakdown potential, the higher voltage the breakdown potential is, the more corrosion resistance it is, right? It is. If, yeah, if it is lower, it means that the corrosion, the breakdown potential the breakdown of the surface begins quicker. The initiation of the corrosion damage begins faster at a lower voltage. So what I would expect to see is if you had areas that were more iron rich and not as chromium rich because of inconsistent passivation execution, or if the passivation was insufficient to create that nice, consistent 20 angstrom thick chromium oxide layer, right? You would most likely see a breakdown potential occur at a lower voltage. Does that help? And the characteristics of curves depend on how the material is behaving to the voltage that is being passed through it.
Great. And I think a similar question along those lines is what areas are medical devices are more susceptible to corrosion?
Okay. So the areas of medical devices that are more susceptible to corrosion would be intersections between two dissimilar materials, right? There you also have a higher propensity for potential galvanic corrosion. If there is a weld or a solder or anything that required some sort of joining, those areas are typically weaker and more susceptible to corrosion, even with passivation. The other aspects are, typically there's more stress in areas of the material that have curvature or sharp edges or geometry. And so those areas are typically more susceptible from a thermodynamic sense to corrosion. So typically when we take Keon's images, digital images of your medical device before and after corrosion testing, we try to find and focus our higher magnification images on those specific areas of the medical device.
Okay, great. Here's an interesting one. How do I go about simulating a 10-year study on a medical device to understand potential corrosion due to contact with medicines or other things?
I think first and foremost, we would need to understand what that medical device is, what it does, right? How often does it do what it does in the lifetime that it's implemented in the body? So we need to understand more like What does it do? How does it do it? What conditions does it affect this, you know, if there are anything that affect the medical device, what environment does it sit in throughout its lifetime in the body, right? And so some ways that, you know, samples are accelerated for this are, you know, I'll give an example. I guess a good example would be stents, or yeah, stents. So it sits on your blood vessels, and how often does your heart pump, right? So I believe there's information out there where we can approximate how often your heart pumps, therefore the oscillation of that blood vessel, right? And so you would take that, you know, and cycle it through this comparable number of cycles to mimic that, and we can test it in the worst case scenario. And then oftentimes temperature is also added. So if it's normally in body temperature, we can accelerate that by increasing the temperature by 1 or 2 factors. So do remember, like, when we run this test, we want to run it in the condition in which the sample sees what the sample would see out in the field. And if someone would like to test something like that has been in the body for 10 years, so depending on what it does, we should mimic those 10 years, accelerate and mimic that, whether it's fatigue cycles, you know, or turning something on and off, right? And then we can exacerbate it by using some temperature. So typically that's how it's done. So, but every case is different. So we would have to kind of analyze the situation and see what those conditions are and brainstorm and figure out like how we can do that. Hopefully that helps.
Okay. Let's move on. Let's see, how do you, oh, the question moved. Are the fluctuations of the human body pH taken into consideration when testing?
Can you repeat that again? I'm sorry, Michael.
The question is, are fluctuations of human body pH taken into consideration during the testing?
No. So it is not taken in consideration during the testing. Now, you can test at different testing mediums. So if for some reason blood plasma, like PBS, is not what you want to test it in, or if you want to test slightly higher, so more basic, slightly lower, 10%, you know, you can do plus 10%, minus 10%, and test in the range. We can run additional testing where there's a high and a low fluctuation. Does that make sense? And then, you know, there are, within ASTM F2129, there are other mediums that it provides formulations for, such as urine, artificial urine. I think you have saliva, but, you know, in certain parts of the body, and when the body are in certain conditions, you know, let's take, for example, like cancer cells tends to have lower pH than normal healthy cells, correct? So it would be best to do some research and see how we can replicate that medium in the correct pH and run the test in the appropriate condition and environment, yeah.
Okay, thank you for that question. There's a question here. How do you determine if the passivation layer is sufficient? Is TOF-SIMS test plus corrosion test sufficient? I think I can answer part of this question. I'll give Ken Ling a break here for a second. Passivation layer thickness can be determined in several different ways. One way that Ken Ling briefly touched upon earlier in the webinar is Auger emission spectroscopy. So that's a pretty common way to determine oxide or passivation layer thicknesses in things like stainless steels, but also other metals like nitinol is another pretty common one that we can do by Auger emission spectroscopy. Of course, we could also do a electron microscopy technique, such as cross-section SEM, or taking a slice out of the sample and examining it by TEM. Those are also possible. I'm not sure if TOF-SIMS would be a great choice. That tends to be good for things like organic materials, but we could, I suppose, do dynamic SIMS or something like that to measure things like oxide thickness. And then, of course, yeah, if you want to test for corrosion using one of the techniques Ken Ling discussed, that would be more of a bulk type analysis, right? Because the Auger, the SEM, the TEM, the SIMS, all of those are just going to be relatively small spot size. We can only test a certain area of your part. We're not going to be testing the entire sample the way that a corrosion test would. So hope that answers your question. I think maybe we'll have time for one or two more. I see that there's a lot, and I believe that if we didn't get to your question during the webinar, we'll try to answer them by email or something afterwards. Let's see. Are there ways to test accelerated corrosion for vascular implants?
Are there ways to test corrosion for vascular implants?
Yes.
The question. I guess we would have to, I mean, once again, determine like what is the material, you know, if we're looking at doing general corrosion testing, corrosion susceptibility testing, F2129 is a good way to test it. So then we would have to look at your sample size, shape, and dimension and see if there are any limitations based on the setup. And then if it's not implantable, right, and it doesn't have to sit in your body for a long duration of time, then the question is, do we need the ASTM F2129 test, or can we do another test if it is something that is reusable or only in the body for a short period of time? I think, I believe like if it's an implantable, then we would, we should be able to test it, but we would have to see what is the material, and what is the size and the dimensions, and understand, you know, more about the medical device that that we're being asked about. So, I mean, for that question, I think it would be best to contact myself, and so we can have a online discussion and learn more about the project and the details related to it.
All right. Have you run stomach acid? Or I guess a different way to frame that question is stomach acid one of the media that can be, or that is, can be used in the F2129 test?
Yes, I believe there's something that mimics the stomach, but I don't know specifically stomach acid. We would have to look into that. But that too would be a great discussion to have one-on-one. If you wanted to reach out to me, I believe my contact is available. Right, Michael?
Yes, I believe
Yep.
all of our contact information will be available to all attendees.
Mm-hmm.
Okay, maybe time for just one last question then. I'm not entirely sure I fully understand what this question is asking, but I think what they're trying to get at is whether or not the F2129 test can indicate or is indicative of corrosion susceptibility for a product that may be in a body for a long period of time. Like, is it going to tell you if the device will corrode 5 years from now, 10 years from now, 15 years from now? Or is it more of an instantaneous kind of measurement?
It's a, so ASTM F2129 is designed specifically to induce corrosion to a preset, like either a maximum voltage or a maximum current density, based on a maximum current or maximum density. So it's trying to create, so it's inducing corrosion damage, essentially. It's trying to test how well your medical device holds up to it. So it will not tell you over time. There's no corrosion rate, let's put it that way, that is determined. But I guess we can determine a corrosion rate, because at the end of the day, we do have a anodic and cathodic curve, and we can build a Toffel curve. So we can calculate that for you if that's what is wanted. But if that is something that is wanted, then the scan rate needs to be decreased to 0.1667 to acquire additional information to get better understanding of the slopes of the curves in order to calculate a corrosion rate.
All right. Thank you all for all of your questions. There are still quite a few questions that we didn't get a chance to go over or touch on, and we will be in contact with you to try to answer some of those questions or any other questions you may have after this webinar. So just wanted to conclude with a little summary about why Eurofins EAG Laboratories is a good testing lab for your devices. First and foremost, client confidentiality is a core of our business. We do almost all of our work under implicit NDA, and we can offer explicit NDAs as well. We have, as mentioned before, a bevy of techniques, over 2,500 instruments worldwide that can be used to help solve your problem or further characterize your samples so that we can identify your problems. We're a global leader for materials testing services, and we do have various accreditations, ISO 9001, 17025, 27001. Yeah, the takeaway is that we can help you solve your materials and engineering related product problems. So with that, I'd like to return this back over to Melissa.
Great. Thank you to our experts, and thank you for attending today's event. If we didn't get to your questions today, we will follow up with you soon. And if you have other questions, please send them to the email address on the screen, customerservice@eurofinseag.com. And for future events and on-demand webinar recordings, please visit eag.com/webinar. Once you leave today's event, you'll receive a survey on the presentation, and we would appreciate your feedback. And on behalf of Eurofins EAG Laboratories and our experts, thank you so much for joining us today, and have a great day.